Okay, so this is where we left off, was here where we're looking at some of the thermo equations and we're combining things like Gibbs energy and E cell and equilibrium constant. We already did the combination of Gibbs energy to equilibrium constant. And now if you remember this equation here, if you plug it into minus NF E0 cell, and you can then derive this equation here where your standard cell potential is RT over, so R gas law constant, which is actually Boltzmann constant times Avogadro's number, then temperature, so temperature in Kelvin or absolute temperature just in general, over N the number of moles of electrons transferred times Faraday's constant times the natural log of the equilibrium constant. And if you want, you can put in the values and you get the standard cell potential is 0.0592 volts over number of moles of electrons transferred times the log base 10 of K, equilibrium constant. And I mentioned here, why are we using logs? There's two reasons. First of all, these different branches of chemistry were developed independently of each other. And then when they started combining them, we were just trying to find standard rules. And that's one of the reasons why, like, so E0 cell is considered positive, is considered spontaneous, where for Gibbs energy, negative is spontaneous. So like I said, they were developed independently of each other. And so the sign conventions just kind of went the other way. And nowadays, of course, with our cell phones and calculators, I mean, all the math is just at our fingertips, and these rules were all joined together from about the 1940s to the 1960s, and we didn't have the sweet calculators that we had. What we did have, though, were slide rules and big books of logarithms. And like, why would you carry two books of logarithms when you can carry one book? So and that's why they converted to log base 10. So natural log is just not as popular in general because, I mean, it's mathematically, it's a better log system, but log base 10, we could use pH in log base 10 and some other thing. I mean, and obviously for electronics here. So, but, you know, things are different now. We don't have to worry about, you know, can you imagine doing chemistry class with your come into class with these big books of logarithms and your slide rules and that kind of thing? I don't even know how to use a slide rule. So I know how to use logarithm tables, but I mean, it's just looking up numbers, really. It's not a special skill set. Okay, and then another equation. So non-standard conditions, you can similarly have this equation here, and this is known as the Nernst equation, where the non-standard cell potential is equal to the standard cell potential minus the 0.0592 volts over number of moles transferred of electrons transferred times the log base 10 of the reaction quotient Q. So, and this is similar to this equation here where you have the standard, the plus RT ln Q. And it's just similar derivation from the top one. So let's use these for some calculations. And let's use the tabulated cell potentials to calculate the equilibrium constant for the oxidation of copper by acid at 25 degrees Celsius. So, and so copper metal plus 2 hydrogen ion acids makes copper plus 2 aqueous plus hydrogen gas. So first of all, if you remember standard cell potentials, yeah, maybe I can even go to that. 20A. If you remember when we were looking at, oh, that's right, 20B. When we were looking at the standard cell potentials. So here is the hydrogen line there. I guess it's getting busy. Here is the hydrogen 0 line and copper, well, copper plus 2. There's 2 of them. I can see one here and then there's one here. Is there copper? Oh, here it is. Here's a copper plus 2. It's right here. So this one right here. So So right away, you know that this is non-spontaneous because copper is above hydrogen. So if it goes forward, it's going to go forward very, very slowly. So that kind of gives you a hint right away. You know that K is going to be a small number. So kind of coming into here, right away K is a small number. So, but we can use the equations, and I've gone ahead and figured out the E0 cell ahead of you. So it's negative 0.34, and it's just because I even can go back to it's because for this one here, it's positive 0.34, this one here, and it's just the reactions in the opposite direction. And the other one, it's hydrogen's 0, so it's going to be 0 is as is, but of course 0 doesn't matter, and then you flip this one going the other way, and then so because of that, this becomes a negative 0.34 volts. So E0 cell is negative 0.34 volts. And then we can apply using this equation here. Standard cell potential is 0.052 over n number of moles of electrons plus the log base 10 of K. So first of all, what does n equal? N equals 2. So n is going to be 2 moles electrons. Because if you look at the half reactions, copper goes to copper plus 2 electrons. Same thing, 2H plus 2 electrons goes to H2. So these are the half reactions, and the number of moles of electrons transferred, it's 2. So n is 2 moles of electrons. And also our E0 cell is figured out, and n is 2. So we can just really solve for K. So, but now I like to do the algebra first. It's however you want to solve the problems. I prefer to do the algebra first. So it's going to be n E0 over 0.0592 equals log of K. And you can take 10 to both sides. So you take 10 to whatever, both sides. So K, look at my K, big K. Of course, my big Ks look like small Ks. So then you just plug in the numbers, 10 to 2 times 0.34 all over 0.0592. And when you put that in your calculator, you get 3.3 times 10 to the minus 12. So not surprisingly, it's a small number. Yeah, question? Oh, that's right. Negative signs. You're right. Forgot the negative. Yeah, no, you're right. Oh, wait, no, then it's not that's positive. This is negative. You're right. No, wait, no. Yeah, there you go. It's all that ham I ate yesterday. Yes. Okay. Other questions? All right, so we have this reaction here. Copper plus 2 hydrogens makes copper plus 2 ions and hydrogen gas. So we go and we look up the standard cell potentials, calculate the standard cell potential to be minus 0.34 volts. And then looking at the half reactions, 2 moles of electrons are being transferred. So we can use to figure out the equilibrium constant. We can solve for equilibrium constant. It's 10 to the number of moles times the standard cell over 0.592. We plug in the numbers, 2 moles of electrons, negative 0.34 volts over 0.0592, and we get 3.3 times 10 to the minus 12 for the equilibrium constant. And even starting out, like thinking about, is this reaction going to go far? And copper in general is a very unreactive metal. And copper, generally speaking, we also know does not dissolve in acid. So I guess it can dissolve a little bit, doesn't go appreciably very far at all. So this, looking at this, we can just calculate that the equilibrium constant is very, very small. Therefore, the copper does not appreciably dissolve in acid whatsoever. So, questions with this one? And again, I'm always amazed, you know, like this is cool. That's the electromotive force in electrons, electromotive force in the electron, depending on what's environment is related to the energetics, not surprisingly, but then the energetics is related to the equilibrium, and the equilibrium is related to the concentration. So that's amazing. Amazing that the force of an electron, how bound it is to the atom, is related to the concentration you see in certain solutions. So who would have thought that? So, all right, and now we'll do a Nernst equation. So determine the cell potential for the electrochemical cell based on the following two half reactions. So we have copper going to copper plus two electrons, and permanganate going to plus acid goes plus 3 electrons, goes to manganese oxide plus 2 waters. Okay, so looks intimidating. How do we solve this problem? So let's start out. Well, let's figure out the equations to use. We're going to do the Nernst equation for this one. It's going to be E equals E0. It's minus 0.0592 volts over N log of Q. That's a minus. So Nernst equation, let me make sure I wrote that down right. So is that the Nernst equation? Oh, here it is. Yeah, that's right. And I'd probably start out by finding out what E0 is. So we already know this one is minus 0.34 volts, right? Because we just did it in the previous problem. So, and I don't have these memorized. I have to look them up. So where is permanganate? This is getting ugly. Okay, oh, here it is. So it's gonna be, oh, and what about the acids? Oh, here it is. Wrong one. It's this one. So there we go. It's that one. You can't use this one because I mean this one there. If you can see it, there's no acids. So you have to use this one here because it has the acids. It's 1.21 volts. So where is this? This one is 1.21 volts. And so, wait, this one's saying 1.68. Do I have the wrong one still? Oh, I do. Jeez. It's this one here. So it's other thing. Make sure you get the right equation. So it's 1.68 volts. 1.68 volts. And so 1.68 volts minus 0.34. This is 1.34 volts. That's our E0 cell. Now, the next thing is we have to balance the equation. So for the, we need to balance the equation to get the number of moles and also the Q. So balancing this equation, we have 2 electrons transferred here and 3 electrons transferred here. What's the lowest common denominator of 2 and 3 is 6. So our complete equation is going to be then 3 copper, because we multiply this equation by 3, and this one, the bottom one, by 2. So a special note, though, when you do this, you do not multiply the standard cell potentials. Okay, so the standard cell potentials, these are intrinsic properties. These deal with the amount of potential that each electron has in its environment. So it is, you do not multiply that at all. So that's a common mistake. Do not multiply the standard cell potentials. The standard cell potentials are completely intensive, meaning it doesn't matter how much stuff you have. So you do not multiply those numbers at all. So do not, I'm being very specific, a common mistake I see. Do not, when you do the standard cell potential, do not multiply this one by 2 and this one by 3. So do not do that. I'm doing that explicitly because I see that mistake a lot. So, but you do have to balance the equation. 3 coppers plus 2. I'll put in the states. So I should. So there's no. I'll be proper today. I normally don't. Copper solid plus 2 MnO4 minus aqueous plus 4, or it's times 2, sorry. 8 H plus aqueous yields 3 copper plus 2 aqueous plus MnO2 solid plus, no, this is 2, sorry. This is 2, 4 H2O liquid. Okay, so I'm writing this explicitly because what is Q? Q is going to be products over reactants. So it's going to be copper plus 2 cubed. So manganese oxide and water, they're liquids and solids. You do not include those in the equilibrium expression. So those are not included. But then MnO4 minus concentration squared is an acid to the 8th. So you do not include the solid copper in the denominator. You do not include the solid manganese oxide or liquid water in the numerator, because those are liquids and solids respectively. So you only include the things that are aqueous. So that is your Q. And I can just go ahead and put the numbers. So the numbers are going to be 0.01 cubed all over 2 squared times 1 to the 8th. So so nice that it's 1 molar. If that was that's a tough number, right? 1, whatever to the 8th power. Good thing it's a 1. Also, what else is our N? What are we missing? N equals, not 3, N equals 6 moles of electrons because of these half reactions. So that the copper generates 2 electrons, the permanganate consumes 3 electrons, lowest common denominator of 2 and 3 is 6. So we are having a total of 6 moles of electrons transferred in this chemical reaction. So next thing we need to do, how are we doing so far? Anybody have any questions? I know this is a long problem. So let's take a midway break. Anybody have any questions about anything? Of course, I'll do a recap. Okay. So midway through, no questions. So let's then do the Nernst equation. E equals E0, 1.34 volts minus 0.0592 volts over 6 log of 0.01 cubed over 4. So I know 10 to the minus 6 divided by 4. So and you put that into your handy dandy calculator and your answer is going to be 1.41 volts. And there's your final answer. So, okay. Recap with this one. So I'm just we're writing this, the student you have in the classroom is writing, so I'm gonna, you're good, okay. So Kiana, Abel, do you need more time or, because I know this is a long problem. Okay. All right, so redoing this one. So start out with the standard cell potential and we look up the values and the standard cell potential for copper is 0.34 volts. For this specific permanganate, and I'm going to go back and show you, it's tricky, right? You gotta make sure you pick the right one because I mean, look, there's a bunch of them. So just with permanganate, right? I mean, you've got a permanganate here. You got another one here. So, oh, and there's another one here. So you have to make sure you pick the right one. And you have to look at the one that we're using is the one I highlighted in the top in blue. And it's 1.68 volts. So make sure you get the right one. Oop. Make sure you get the proper one there, 1.68 volts. So since copper is going the other way, you flip it to minus 0.34 volts. And your standard cell potential for this is 1.34 volts. So then we balance the chemical equation. So for copper is generating 2 electrons and permanganate is consuming 3 electrons. So you multiply the top equation by 3, the bottom equation by 2. So we get a total of 6 moles of electrons transferred in this chemical reaction. And then we write out the chemical equation in the long form here. And then we write out the Q value. It's products over reactants raised to the stoichiometric powers. So we do not include the solids or liquids in this. So just the aqueous and the gases. There's no gases here. So then our Q is copper plus 2 cubed over permanganate squared times acid to the 8th power. And which is nice, acid is 1 molar, so that just gets rid of that what's all together in a way. And then we apply it using the Nernst equation. So standard cell potential is already 1.34, so E equals E0, which is 1.34 minus 0.0592 volts divided by the number of moles of electrons transferred, this case 6, times the log base 10 of Q, which is 10 to the minus 6 over 4. So whatever that is, and you get the whole standard, the whole potential for this is then 1.41 volts. So, okay. So let's talk about what this means. Anybody have any questions? All right, no questions. I know this is I'm trying to be very explicit with this one because this is one of the concepts students have a hard time with. So the I think students I think the hardest concept is when you determine the rate law from data. That's probably the hardest thing in this semester. I think the second hardest thing is probably writing equilibrium expressions for acids. Students have a really hard time with that. I think then it's probably a tie for the third and fourth most difficult thing in the course is the Nernst equation and balancing oxidation reduction reactions. So these two things kind of bug students the most. So that's why I'm kind of taking my time here. And frustratingly enough, the most common mistake is calculating the standard cell potential incorrectly, because the students tend to multiply the standard cell potentials by the stoichiometric ratios. So that's the more common mistake seen. But remember, it has to do with the electromotive force of the electrons. It doesn't matter how many electrons, it's just individual for each circumstance. So, okay. And so let's look a little bit more at this Nernst equation right here and a couple features of it. So if you look at this Q and why are we not surprised? And like, so if you look at this, like, well, the potential of this battery is higher than the standard. Why is it higher? Well, mathematically, if you're looking at this value, you're taking the log base 10 of 10. So this number right here, that's 10 to the minus 6. So the log of 10 to the minus 6, is -6. I mean, it's going to be a little less than 4. So it's this number here is somewhere between -5 and -6. So and if that's negative and you have a negative here, that's going to turn into a positive. So that tells you some things about batteries. So meaning this is a fresh battery. So if you think about it, so as this reaction goes on, so you have copper metal and it's going to copper ions. As this battery as that copper anode is corroding, that's the anode, it's going to corrode. That means that this number is going to go up. So the copper ions are going to increase in value. And now the cathode, and so permanganate's the cathode. And as this reaction is going, this 2 molar, it's a reactant, it's going to drop. So we're going to lose that value. That's as this battery goes, it's going to keep on going until the copper is corroded or all the permanganate disappears. So it's one of the things that's going to happen. So that's the battery's going to go until it dies. It's going to die because anode goes away or the cathode just runs out of reactants too. So, and as this is going, so the copper ions are increased in value, and then the permanganate's going to decrease in value. And what does that mean for Q? So Q is copper. So as that number gets bigger, and the permanganate gets smaller, as this reaction goes, Q is going to become a bigger number. And as Q becomes a bigger number, right, this term becomes a bigger number, and eventually then the potential of the battery, the voltage of the battery, is going to decrease. So as the battery is discharging, the potential decreases. But this is not surprising now. This is not a surprising thing to hear, right? Because you realize that when you have batteries, right, a lot of things, although I guess we don't have as many toys that have batteries these days. I guess you do certain things, drones, if you have remote control cars. I remember some of the toys growing up, you know, like the things that like kind of dance or something like that, or like have sound to it. They're like, they go and like they're playing a song, like dee, dee, playing a song and dee, dee. Or you have someone dancing like, I'm dancing, I'm a toy, and now I'm dancing slower. I'm singing a song, and now and I don't move. So because as a battery is getting close to dying, it puts out less potential. And eventually the potential gets to a small enough value that whatever the electronics that you're using just doesn't work. So, but you can kind of, sometimes you can have that kind of slowly, you know, it's just not moving very fast. And then it kind of stops. It's like that with my Roomba. I didn't get a Roomba. I got an Elfie or something like that. It's the cheap Roomba. Because you know I'm lazy. I don't like to vacuum. So if when I let that go, I mean it starts off with lots of power, and then when the battery runs off, it turns off the vacuum and just kind of slowly moves around looking for the plug to recharge, right? So that's what happens as the batteries go. It puts out less power, so not surprising. But we kind of already knew that. But now you see the math. You see the math behind it, and the math behind it is the Q, this non-standard Q. As the products become big and then the reactants become small, Q becomes a bigger number, which means this standard minus the Q. As Q gets bigger, or the numbers times the Q, the log of the Q, as Q gets bigger, that negative number gets bigger, and then the potential of the battery drops. So, all right. Questions? So let's see if you can solve this problem. So we have a different battery. So iron +3 aqueous +3 magnesium solid makes 2 irons +3 magnesiums. The iron concentration is 0.001 molar, and the magnesium ion concentration is 2.5 molar. And there's the standard potentials for iron and for the reduction potentials for iron and magnesium. So what is the non-standard voltage of the cell? Still at 25 degrees Celsius, but what is the non-standard voltage of the cell at these conditions?
On the reactant side, it's solid. On the product side, it's aqueous.
You done? What'd you get? Okay, well, close enough.
Yeah, the multiple choice testing. It's
Oh, it's not 2. I'm sorry, it's 6. Okay. Okay. The correct answer is B, and there's a setup there. It's standard cell potential. I 0.0036. If you want to keep on going, the thing is, I guess by proper convention, you should bring it to 2.33 volts for your standard cell, and then have it be then looking at the equation is already balanced. So Q is going to be magnesium plus 2 cubed over iron plus 3 squared, and iron plus 3 is 1 millimolar, 10 to the minus 3 molar. Magnesium is 2.5 molar. So 6 moles of electrons transferred. So it's going to be 2.33 minus 0.0592 over 6 times log base 10 of 2.5 cubed over 0.001 squared. And I know you guys on Zoomers, I guess I didn't really poll you, but do you have any questions on anything? Do you have any work that you get stuck on? Any questions? And I'm taking my time on this. Like I said, it's because students have a hard time with this. Besides the fact that this kind of combines a lot of things, it's not, I mean, there's only going to be like one question like this on the final, but the this gives a lot of other things. The standard cell potential, it's balancing the oxidation reduction reaction. So like this problem, is kind of the union of most things you've learned in this chapter, plus combining the equilibrium from previous chapters. So that's why I'm kind of like taking my time. If you have any questions, let me know so we can work on it. Anybody have any questions? No. Okay. All right. I'm assuming then you understand this perfectly, and you're going to get big fat A's on the final, which would make me very, very happy. Okay. So let me show you an interesting thing. So when you have, if you have the Nernst equation, so Nernst equation is standard cell, the regular cell, standard cell minus 0.0592 volts over the log of Q. You can have a really interesting situation where you can have something called a concentration cell. So if I were to take 2 pieces of copper and stick them in to 1 molar solutions each and put a salt bridge between these 2 beakers, and if I hook this up to a voltmeter, not surprisingly, nothing would happen. There would be no electrons transferred, nothing will happen. But you can get a circumstance like this where you have a concentration cell, and if you can see this, same idea, but we have a dilute here on this side. We have a dilute copper solution, and on the right you can see it's a little more blue. Copper tends to be blue. It's really pretty blue. I like copper solutions. They're nice, pretty blue colors. And if I were to connect this up, and you're thinking, okay, what's going to happen? And we see, oh wow, there's actually a little bit of current flowing. So what happens is, if you set this up, this is the anode. This right here is the anode. It's going to corrode, and it's going to, and I'm doing it for like, dramatic effect. And then this solution is going to become slightly more blue because more copper ions are dissolved. And this reaction, this is the right side around the cathode. So we're going to grow some copper on there. And do I have white? I guess I do. And then this solution is going to become, oh, it didn't show up. Oh. My white highlighter doesn't work. All right. Does it work here? Okay, it does work there. Okay. I guess it's just so faint. So I'll do it this way. Over time, as this reaction goes over time, the solution, if you could see what I'm doing, I highlighted it. It's gonna become more white. or more clear. As it goes on, that solution is going to become more clear, and it's going to keep on going. This reaction is going to progress until these two solutions end up being the same concentration. So, and that is known as a concentration cell. And non-standard conditions. And how does this work? Oh, did I move it? So if you look at the standard reactions, the E0 cell, the E0 cell is 0. So we have copper going to copper plus 2 electrons, and then the reduction reaction on the cathode is copper plus 2 electrons because it goes to copper. I mean, these two reactions, they're exactly the same reaction, so they cancel out. So the standard cell potential is 0. But with the Nernst equation, this 0.0592 volts over number of moles of electrons, in this reaction, it's 2 moles of electrons transferred times the log of the Q. So it's product over reactants. So it's whatever 0.01 over 2 molar, and so we get a slightly positive voltage out of this. So right there, and that's a concentration cell. So what? Why do we care? This is kind of fascinating, but do we care? Well, one thing that we use for concentration cells is a voltmeter, or not a voltmeter, a pH probe. So you ever wonder how pH probes work? And one thing with pH probes, you notice they always have them connected to electronics. And the way that a pH probe works is you have a area in the probe, and if you've ever seen a pH probe, they're like wands. They're maybe like quarter of inch thick tube, and on the bottom of the tube there's like this glass bulb, and there's also this like kind of other dot on them. So you see like there's a glass bulb, and if you look close enough there's a wire, and so a wire and a glass bulb, and then a another kind of circular thing. So you do have a wire sticking out of a glass bulb that connects to the solution. So it's electrically connected to the solution. And you have the other thing that you see on the probe looking at it, you have a salt bridge. So it's usually like this little fuzzy thing. So you have the salt bridge here, and inside of the voltmeter, inside of the pH probe, I keep on saying voltmeter because it is a voltmeter, inside the pH probe, you have a solution of acid, a known solution of acid, and then also inside of it you have a voltmeter. And that's actually what the pH probe is. It's a voltmeter. And you can also calibrate it because over time, the acid solution is going to change concentration. But so you can calibrate your voltmeter by looking at the different. You use buffers, usually three points. It's like 4, 7, and 10, or something like that, or 12, or 9, or something like that. It's for when you calibrate them, and that's just to calibrate the voltage to the pH. But essentially a pH probe, it works off of the concentration cell potential, and from that from doing some math, right? I mean, from this, right? If you look at the other way around, if you know the standard cell is 0, if you know the E0 cell and you know the moles of electrons, it's going to be 2. And if you know one of those, then you can calculate the other. It's one equation, one unknown. So what the pH probe does is it uses the voltage to calculate the hydrogen ion concentration. So from this, the voltage will give you a concentration of hydrogen ion concentration, which you can then, minus log gives you the pH. So that's how a pH probe works. If you ever wonder how the pH probe works, it's a concentration cell. And it works off of specifically the Nernst equation. This Nernst equation right there. So that's one application of this. And the other very, strong application of this are batteries. So, and here is a dry cell battery. And so when you look at a battery, has anyone ever sawed a battery in half? I have. No one's done it. Be very careful if you do. So you can take a battery, and it's hard to do because you can take a hacksaw, and you can take the battery, and you can just take the hacksaw and cut it down, and it's kind of hard to do. At least I found it kind of difficult. And when you slice the battery in half, well, I've done it to an alkaline battery. I'll show an alkaline battery in a second. This is a dry cell battery, and in the middle of the battery, you have a carbon rod. So a carbon rod, and that's also what sticks out on the nipple part of the battery. So that the positive terminal, that nipple that comes off, if you slice into that, you'll find a carbon rod. It doesn't connect all the way down. You can see there's some space there. And then you have the outside of the battery is coated in zinc. And when you have the battery, so this is the positive end, and then this is the negative end of the battery. And when you have it connect up to a circuit, right? Well, we say that the current flows this direction. Of course, as you know, that's wrong. It's really the electrons. The electrons really flow this direction. But for the current flow goes from positive to negative. And so I guess the current flow is going to be that direction for electronic diagrams. But like I said, as we know, they're wrong. But what is happening here is the zinc on the outside of the battery is going to corrode, and there's this moist paste that has magnesium oxide and ammonium chloride in it. So that acts as the salt bridge, and the zinc comes into zinc ions in a solution, and then I don't know which reaction this one's going to be. Magnesium oxide, it's going to do something. So, but most batteries now we use are alkaline batteries. So, and the difference between this and an alkaline battery is it has potassium hydroxide in it, and that means it's basic. So opposite of acidic is basic, right? And another word for basic is alkaline. So an alkaline battery. So same idea, but you have to be careful. So if you are to saw apart, what you do not want to do with batteries, you do not want to saw apart the battery and then rub your eyes, because bases really, really damage your eyes. And another trick, if you do decide to do this at home and you get anything in your hand, make sure see if your hands are slippery. So whenever I do this, I get stuff on my hands. Or whenever I work with batteries, like the batteries explode. Like if I look at my remote doesn't work. I open it up and I pop out the battery. It's bursting and it's got this goo on it. So I pick it up and my fingers feel all slippery. I'm like, oh crap, That's an alkaline battery. I got potassium hydroxide on my fingers, and I put my finger under running water, and for 20, 30 seconds, I just put it in the running water, and I just feel it back and forth. And when it's no longer slippery, I know it's safe. So that's what you do. And if the potassium hydroxide goes and leaks into somewhere, and like there's usually terminals, and I found that sometimes the terminals get corroded. I take Q-tips and I dab it with vinegar, and then that usually then it cleans it, and then that tends to you have the right connection, because you have to have an electrical connection. If you have a terminal, it's all corroded, it's going to turn into a salt, right? So a metal and a non-metal salt, and solid salts are not going to conduct electricity. If it dissolves in water, then you can have an electrolyte solution that dissolves, but solid salts don't conduct electricity very well. So that's one of the ways you can fix up old things. So if corroded, like calculators or remote controls or stuff like that. But be careful with the vinegar though, because if you get electronics wet, sometimes they don't work. So, and typically speaking, the alkaline batteries, they die when the zinc goes away. So that's typically what's the limiting reagent is on the alkaline batteries, is the zinc. And so problem with alkaline batteries is, I mean, they're light, they're cheap, they're great, but they're not really easy to recharge. So they're not very rechargeable. And we have other types of rechargeable batteries, and one specifically that we use quite a bit in recharging is a car battery. So, I mean, I use my car very frequently, and your car, I mean, its primary power source is the internal combustion engine. So, but you need to start the car, and also it's nice to have certain things always have electricity to it, like the clock, have the clock keep on going, but and also the storage for your radio, that kind of stuff. But we have a car battery, and the car batteries are also known as lead acid batteries. So, and a car battery is a 12-volt battery. It's actually 6 cells. It's 6 cells at about 2 volts apiece, connected in series. And so if you were to take a power, I've never done this. So I've personally never done this, because I am probably because you can get money back for your batteries. Because like when you buy a new car battery, you can take the old one back, and they give you whatever, like $9 back or something, like whatever it is. They call it the core. And besides the fact, I don't want to dispose of it. So I don't want to have to deal with a heavy bucket full of sulfuric acid. So I'd rather I've been lazy. I've just been giving them a battery back. I haven't taken it apart yet. But if you pick up a car battery, you might notice a couple things. First of all, they're heavy, right? Car batteries are heavy. Why are car batteries so heavy? Because among other things, they've got lead in them. Lead is heavy. Also, if you take a car battery, you might, like if you shake it, you can kind of, oh, there's liquid in here. You feel like a slosh, 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 slosh. And what car batteries have, they have battery acid. What is battery acid? It's sulfuric acid. So 30% solution sulfuric acid, that's about 6 molar. Okay, so 18 molar is 100%, so 30%, about a third. So it's going to be a little less than 6 molar. That's pretty concentrated. So 6 molar sulfuric acid, that's kind of scary. That'll melt your skin. So blind you really fast and melt your skin. So be very, very careful with car batteries. And So if you already take a car battery apart, like I said, and I've never done it, but what you'll find is you'll have two screens, and if you take the screens out of the sulfuric acid, one screen is going to be white. And this is a fully charged battery. One screen is going to be white. That's going to be the lead oxide. That's the cathode. Lead oxide is white. And the other screen is going to be kind of a dull gray color. The dull gray color is metallic lead. So as the battery is going, if you fully dispel the battery, all the lead metal is going to go away, and all the white lead oxide is going to go away, because the white lead oxide turns into lead sulfate. And this is lead, it's lead +2. This is lead +4, and yeah, so lead +4 goes to lead +2. Lead metal goes to lead +2, so it's 2 moles of electrons transferred. And the lead sulfate is aqueous, so it goes into solution. And then what's nice about lead acid batteries is that it's really easy to recharge. So if you turn it around, I guess you put the currents, I mean, really the electrons go that end, but if you push current on this end of the battery, it's going to recharge the battery. So, and lead acid batteries are very easy to recharge. They're fairly inexpensive, and they tend to last a very long time. So they're pretty robust. So, and they don't respond, like for instance, they don't respond as heavily to overcharging as other batteries, like lithium ion batteries, for instance, do not do well with overcharging. Lead acid batteries, these are tanks. These you can hit them with a lot of things, and they keep on going. I mean, they eventually have to replace them. Although I had a battery that lasted for like 9 years. No, not about 5 years. It wasn't 9 years. About 5 years. I had a battery. I don't know. It was just a random Costco battery. It lasted for 5 years, and then it didn't work anymore. And then I've had to replace the battery about every year or year and a half now. So it's pretty easy to do. Pretty easy to replace car batteries. So, so another thing that can happen with car batteries. So we have this thing, it's all in solution. If this electrolyte goes down, the level of the electrolyte goes down, and when that goes down, you have less contact. So there's going to be less. Oh, you can't see that. Oh, you can't see pink either. Can you see white? Okay. Nope. All right. I'll just have to draw it. You have less contact here. And I'm drawing the blue line as the water level, the acid level. If you do that, you have the contact levels going down. So that's another common problem with car batteries, with lead acid batteries. Sometimes you have to put water into them. I've never had this happen. I've never had that happen. So some of these batteries have vents for the hydrogen. So because you can generate hydrogen in this. So, well, I guess they all should have vents. But so the water can evaporate. So sometimes they tell you to add more water and then bring the level back up to make it work again. But I mentioned hydrogen gas. If you connect up the battery in the wrong terminals, especially if you, when you do like a jump start a car, or just in general, there is a slight chance that you can form hydrogen gas and that the battery will explode. So just by pressure. And if it explodes, now you're going to have sulfuric acid. So you're having your sulfuric, if your battery explodes, you're having a sulfuric acid solution coming out of there. So there have been many people that have been blinded by this. So for me personally, I even ask my neighbors sometimes, I'm like, do you think I'm weird? Like, oh yeah, you're weird. Because if I ever work on my car, I wear safety glasses. I mean, I have chemical safety glasses, so I'll do that. I'm just protective of my eyes. You know, like I'll have, if I work on my car, I have gloves on and I have safety glasses on. So, and I don't care. And I know my neighbors think I'm weird, but I don't care because especially, even though doubly, especially with car batteries, because that acid gets in your eyes. You're blind. I mean, there's no going back with that one. So, I mean, yeah, if you get sprayed in your face with acid, you might get some horrible scarring. But the good news is that you'll be able to see people's reaction because your eyes will still be protected from your glasses. So please keep that in mind. And not only that, I guess when I do jump start a car, I'll have the glasses on and I'll even kind of, when I attach them, if I'm backing up and with the full length of my arm, when I attach the cables to it. And then when I say turn the engine, I'm like, okay, then I take a couple more step back and then I'm like, okay, now turn the engine over, because what I'm doing each of those times is I'm trying to keep the as far away from the sulfuric acid as possible. And some people are like, oh, I'll put it in there and stick my face in there. Cool, turn it on now. I want to see the engine run. Don't do that. I mean, that's just because in the slight chance that it does explode, or if you put something together wrong, I mean, that can explode. So, and I'm very protective of my eyes. So that's a car battery, at least the common, the lead acid car battery that most gasoline cars have, and also diesel engines. They tend to have lead acid batteries to help them turn their engines over as well. We have lithium ion batteries, and I guess I'm looking at the time. I guess we're about done. So I will pick up and talk about lithium ion batteries on Wednesday then. So, and the other applications for batteries. So anybody have any last? Oh, there's my shut up alarm. Shut up alarm. Anybody have any questions? No questions. Okay. All righty. I'm going to stop recording.